Hello everyone and welcome back. Today's lecture is going to be about linear regression. Linear regression is a very important algorithm to first introduce basic concepts such as a hypothesis, optimization, gradient descent, and the like. All of these concepts will be very important for the future for more advanced machine learning algorithms. So the first step to get into any machine learning algorithm is the data. What does the data look like? What does it represent? And one of the most basic ways of collecting data or of representing data structures is a table. So you have a table of numbers, and let's say it's organized in that way. You have columns and rows. Typically, each column represents a feature of the data, and each row is an example. So let's think of a specific example. An apartment. So you have a set of data that represents different apartments or different houses in a city or in a town or in a country. And each apartment is represented as a row, and each feature in that apartment is a column. So the apartment can have a different size. Let's say X4 will be its area. X3 will be the floor, on which floor it is, 1, 2, 3, etc. Could be the location, it could be the price, or different features. And the question is, what would you do with that data? If I just give you this data set, the first thing you can think of, what can you do with it? So here now each row, as you can see, is an apartment. So you would have n apartments. And as you can notice, just notation-wise, this is important also to start with, the subscript represents the feature number, and the superscript with parentheses represents the number of the example. So each row now is called an example. Now the first step is to just look at the data, try to understand it, visualize it. You can also calculate statistical metrics. So you can take, let's say X4 are the prices of the apartments. What's the average price? What is the distribution of the prices? So all of these techniques for understanding the data are very important to start with, to have some insights as to what do you want to do with that data. So also cleaning is very important as a pre-processing for the data. It might be that some features are missing and you just want to completely drop these apartments, or maybe they're not representative of the data. You're not interested in that type of data. So first of all, we're going to, before we look at what you can do with just a table with no inputs and outputs, let's imagine that you have a scenario where you have inputs and outputs. And what I mean by inputs and outputs, I mean things that you're interested in predicting. These are the outputs based on things that you have. These are the inputs. All right. So given the input, let's say I give you X1 and X2, what is the output that is unknown? So the idea is I give you a set of apartments that are known, where the inputs and outputs are known, and now given a new input, I want you to predict the output. Right? So this is the basic idea behind supervised learning, whether it's linear regression or anything else. And so often this new input that's given to you is called the query, and the thing that you want to predict is called the prediction, obviously. Now let's represent this problem a little differently. Here I'm assuming that I have two input features, X1 and X2, and this X. And here implicitly I assume that X is actually a vector that contains these two elements, X1 and X2. And the output is also a vector that has also two features. I'm assuming that just to be general enough that I'm saying Y is not the scalar, it's a vector. And what I'm really interested in is, given the data, the table that I just showed you, I want to find the function h, which is also called the hypothesis, that predicts the outputs y given the input x. So that if I give you a new input x, now you can predict the output y. Right? And a lot of machine learning, specifically supervised learning, is concerned with this type of problem. Find the function h given input-output pairs, x, y. Right? So this is what supervised learning is about. And you can rewrite this statement as just the simple function y is equal to h of x. I want to find h. All right, so let's now simplify things a little bit, where we say I have one input and one output, right? I assumed first that x and y can be vectors. Now I'm just going to start simple with, let's say the input is the size of the apartment and the output is the price of the apartment. And you can imagine that they're correlated to a certain extent. And so the bigger the house, the more expensive it is. So now I have a new input, xq, the query, and I want to predict yp, which is the output. Right? So first thing, as I said, the first thing you want to do usually is visualize the data. And so you have input-output pairs, and each one of the rows now is a point in this Cartesian coordinate, input x, output y. Right? So, and you have this spread, and as I said, you imagine some kind of correlation where as you increase the size x, you have a higher price for the apartment. And the question, when I ask the question, what is yp given xq, it's really, the question is, I give you xq, so now you go up and say, well, where is yp? This is the prediction. So one way to do it, I would say, maybe before I show you the next slide, I already did, but think about it. How would you do it? Right? If I just give you an xq, a new apartment with a size, and I give you the data as well, what is the best prediction? Right? And here there is no unique answer. This is a very important thing to understand in machine learning. There is no unique answer that depends on what kind of h you're interested in. You have to make some assumptions about h. Maybe you'll think it's going to be somewhere in this area. So what if I just take these points and average them out? Right? So this is what is going to be called a k-nearest neighbor algorithm. Has this type of logic to it. And you don't really need the function h. All you need to do is look at the closest points and then estimate what the output will look like. So, a simple version of that is a weighted average of the surrounding points of the two closest points. The one that's closest to xq from below and the one that's closest from above. So k nearest neighbors does that. But what about linear interpolation? Why can't I just interpolate all the points and then you would get some similar result where you just connect a line through the points that are before and below and above xq, and then just make the prediction for y based on that. Why is that not possible? It is, of course, possible, but the question is this the best strategy? Will you get the actual best prediction for it? And here I added mathematical notation that you need to think about. Usually you will see that written either in papers or in books, that what we're doing is we're trying to come up with an a hypothesis that's mapping a real number to a real number, right? And because these are two scalars that can be any value between minus infinity and plus infinity, we're mapping r to r. And this is what is going to lead to linear regression. This is the constraint we're interested in. We're not predicting a 0 or 1 or a binary value, but rather a continuous value that goes from minus infinity to plus infinity. Now, let's think of another strategy. How about polynomial interpolation? Right? Maybe linear interpolation has these discontinuities in the derivative, and you want to be a bit more sophisticated and have a spline or polynomial interpolation. Of course, that's also possible, but is this the best thing you can do? So all of these questions, I want you to think about them, maybe pause the video and try to think, well, you're given a bunch of points, you're trying to find the function that allows you to predict outputs given new inputs. What would you do? Right? And this question is really the fundamental question that underlies all of supervised learning. And it will lead to really hard problems to solve in machine learning that are really not fully solvable, and that will always, this question will always haunt you to a certain extent, depending on what algorithm you're using. So it could be that this function that you're looking for is not really passing through all the points. It's some vague regression through the points, and it might be a line, it might be something else. So how do we choose these points or this hypothesis? So we're going to start with something really basic, which is a linear function. We're going to assume that we just have a line. It looks like they're correlated, and so the simplest function we can assume is a line. So h is just a line. So what does it look like? So pause the video a little bit and try to think, how would you express h as a function of x? right? What is the function? What is an equation for a line? Now, h, if it passes through the origin, then it's h equals ax, or you can say that y is proportional to x, and a is just the constant of proportionality. But this is assuming that the line passes through the origin. And all we need to do in this case is find the a, the coefficient a, which is now here, it's called a fitting parameter, that actually allows you to approximate the trend as well as possible given the data. Now, if you want this trend to be shifted, right, in the case of apartments, for example, is it passing through the origin or not? So the input is the size, the output is the price. If the size is 0, is the price 0? Well, it seems like that's the case, right? You can't have an apartment that has a finite price, but its size is 0. So this could be a good hypothesis for an apartment. Of course, you'll have more features than one input x, but here we're just starting simple with only one input. So let's say you have a case where you have a y-intercept. Therefore, there is a finite value when x equals to 0. So y has a finite value when x equals to 0. So in this case, the hypothesis becomes y equals ax plus b. Now, back to the original question, what are the best a and b that fit the data? And in this case, when we ask that question, a and b are called fitting parameters. We're trying to find the best a and b that fit the data as well as possible. Now, I'm going to change notation a little bit for later, and this will help us make the notation more compact. So, first of all, instead of using a and b, I'm going to use theta 0 and theta 1. So these are also scalar, and theta 0 and theta 1 will be part of a vector theta, and the hypothesis now is parameterized by h of sub theta, right? The subscript of h now indicates what are the parameters that we're really trying to change in order to fit the data. I can rewrite this hypothesis as theta 0, theta 1 in a vector dotted with 1x in a vector, and these will contain my features, my inputs, and my pre-processed inputs, where I added 1 here, so to account for the bias, what's called the bias, theta 0, and then you'll have a parameter vector. So these are unknown parameters that I'm trying to find, and these are my input features, or sometimes called attributes. So now I have theta.x, where theta is a vector, x, my new bold x, that sometimes I'll just call x, is also a vector, and this is my feature vector. So it's sort of, I took this input, I pre-processed it into a vector so that I account for the bias, and now I have theta.x. And you'll see that when we go to higher dimensions, this still holds true, where I have more inputs in this input feature vector and more parameters there. All right, so the next question is, I've decided what my hypothesis is. I've decided that this is a linear model, it's just a line. And the next question is, how do I find the parameters? Right? How do I find theta 1 and theta 0? What are the best theta 1 and theta 0? So also pause the video here and think about it. Think, what mathematical construct can you come up with that gives you what you would consider to be the best hypothesis? And this is a really good exercise before you see the solution or you continue the video, because it will train you to think about what are the best mathematical tools that you need in order to solve problems like these. Because it might be that you've never seen these approaches before. When you think about it a little bit, it'll help you, it will stick better when you see the solution. All right, so what happens before we get there? What happens if you have more inputs, right? We're still at the stage of defining a hypothesis, and I have x1 and x2 now as inputs, and I have one output y. So I just one output rather than two. So now x here is a vector. It's not a scalar anymore. And I can still define a linear model that way, where I have theta 0 plus theta 1 x1 plus theta 2 x2. And in the case of if I have only x2, then I don't have x3 and above. But you can imagine having as many inputs as you wish. I can rewrite this as a vector. Now I have theta 0, theta 1, theta 2, theta 3 in the first vector, dotted with 1, x1, x2, x3, which is the second vector, which contains all the attributes, right? So this is my feature vector, this is my parameter vector, and they're dotted with each other, and this is the linear hypothesis, right? It's linear in x, and it's also linear in theta. And these are the parameters, fitting parameters here. I'm introducing new notation or names because people will use different names in different contexts. So these parameters are sometimes called weights, and the features are this vector x. Remember, sometimes I'm not explicit about saying what this x is. It might be a scalar, it might be a vector, so this will depend on context. Sometimes people at the beginning will say, well, x is a vector, and it contains n features, and therefore you have to think that it's something that you can dot it with another vector. All right, so let's write it now. Again, the hypothesis is theta dot x, or what's also written as theta transpose x. So this is a linear algebra notation. Remember that vectors in general are column vectors. So they're column vectors, which means that they have values vertically. They're stacked vertically. And theta transpose means that you turn it into a row vector. And x is also a vector, and it's a column vector, because by default all vectors are column vectors. Then you'll have a row by column, and in linear algebra, whenever you're doing matrix multiplication, or this is called an inner product, you'll have theta 0 multiplied with 1, theta 2 multiplied with 2, etc. So you have a row vector multiplied with a column vector, and this is just the same or equivalent to a dot product. All right, so where do we go from here, right? So we're going to go to the original question that you hopefully thought about a little bit, and we're going to ask, how do you pick the best parameters? So I have this line, and I want to find the best theta that gets me to this ideal line. There's some concept of a line that's really capturing the trend of the data. All right, so let's look back at the hypothesis. So theta transpose x. I'm going to write this is another notation, which is the definition of a dot product, which is just the sum of theta I xi, where you go theta 0 x0, here I'm assuming x0 to be actually 1, plus theta 1 x1, plus theta 2 x2, etc. Right, so that's my hypothesis. And based on that, I'm going to define three quantities here. So I have xi, that's for the ith example, ith apartment. And then the prediction for that xi from the hypothesis is just h theta of xi, and the true value is just yi, right? So I'm giving you input-output pairs, that's xi, yi, for the ith apartment, and given the hypothesis, I'm predicting that the price should be h theta of xi, right? So I have these three quantities, and you can imagine that what I'm trying to do is minimize that distance. I want this line to be as close as possible to the prediction to be as close as possible to the true value. So how do I actually do that? I want to calculate some kind of distance between h theta of xi and yi. And how do I do that? You can see that these are the green dotted lines are computing these distances between the prediction and the true value. And I want to quantify that mathematically. So again, pause the video, think about it. How would you quantify the distance between the prediction and the true value? So first, let's find something called a residual. The residual is just the difference between h and y. So you can imagine that, well, let's just take the differences, because that's what I'm interested in, sum them up and minimize the sum of differences, right? The sum of what I'm calling here residuals. Why is that a problem? Is that a problem in the first place, right? If I just minimize the sum of the differences. Pause and think. Well, another thing, of course, if you thought about it, the problem is that the absolute, the residuals will cancel out. If you have a positive residual and a negative residual, so what's below the line and what's above the line, these will cancel out. So it might be that you have some line that's not really capturing the trend, but the negative and positive values are canceling each other out, and you'll have a very small sum of distances. Right? But so what we're really interested in is the absolute loss, and to do that, or the absolute distance, and to do that, you can just define something called the absolute loss, which is just the absolute value of the residuals. And another way to do it is just to square the residuals, and if you square, they're all going to be positive, and it will basically compute the sum of these, dotted line distances that we're really interested in here. So we want to minimize the sum of distances. So let's define these distances, and I will say in a minute why we're calling them losses. So we're going to define a cost function, or sometimes also called a loss function, j of theta, and j is just half, some quantity, constant half, times the sum of the square distances, the square losses, or the square of the residuals. Right? So, first of all, we explained, or we tried to think why this is an important function that we want to minimize. Why? Because we want to find the thetas in such a way that this function is minimized. And the reason we call it a cost or a loss is because we want as little as possible. We want to minimize the cost or the loss. We don't like to lose, so we want to minimize losing, right? So how do we do that? That becomes the question. How do you minimize a function? Right? This is just a function I want to minimize. And remember, what is h of theta? It's right here, right? It's theta transpose x. It's theta 0 plus theta 1 x1 plus theta 2 x2 that you can just replace here. And then you have these thetas that you're minimizing over. So how do you minimize a function typically? And what does this function look like? So these are many questions. Pause and try to think, draw the function, replace the values, and try to come up with an example, maybe of this for this line, and try to imagine what this function looks like. So here I'm just replacing, and we're going to see now what the function looks like. This is sometimes called ordinary least squares. We're minimizing, it's the least of the squares of the residuals. Typically, this is often used in linear regression, but as you'll see later, also in more complex algorithms and models. So how do we choose theta? The best theta that minimizes the loss function, j of theta. So we have this cost function, and we want to plot it. And I'm going to simplify things here a little bit as well. For a start, we're just going to take one parameter, theta j, right? And we're going to assume that function is only a function of one parameter, just like we did at the beginning with h being equals to ax, where it was only a function of a. Now, the function, I will assume, will look like this. Is that accurate? Is this what the function looks like? Right? Is it just like some bowl-shaped function? And is it always like that? So try to think about that. Pause the video, think about that. Well, in reality, if you replace things a little bit here and you assume some values for theta 0, theta 1, and theta 3, and theta 2, whatever the parameters are, you will see that this is always going to be a parabola because it's squared. So indeed, the function is always going to be a parabola. For one parameter, it's going to be a parabola. For more parameters, you'll see it's just a higher dimensional parabola. So the question is, how do I find this point? I'm interested in the minimum of j of theta, right? The theta that minimizes my j of theta. So the first quantity you want to care about is derivative. So what you can do is just calculate the derivative of j and set it to 0. This is how you find the minimum of a function. This works for the square function. It doesn't work for the absolute loss. Think about why it doesn't work for the absolute loss. In the absolute loss, these are going to be straight lines, and it's not going to be differentiable at 0. So setting this kind of function, the gradient of some function that is not differentiable to 0 is not going to work. But let's focus on the square loss for now, right? So you have derivative of j with respect to theta. And this is really, at any point in theta, this is just going to be pointing upwards or in the steepest ascent. In 1D, this is just this vector that's pointing away from the minimum. And what you really want to do, if I want to design an algorithm, right? Let's think about that. Let's say you want to design an algorithm that takes you, I'll give you some random theta, and then you want from that random theta to get slowly to the minimum, to the theta that gives you the minimum j of theta, right? How would you do that? And can you use this derivative? And this is a really important algorithm that's used everywhere. So if you pause and think about this algorithm, you'll remember it forever. So let's start from that. Initial guess, right? We're going to guess the initial theta is going to be my theta naught sub j, right? The sub j is just assuming I'm taking a feature j with parameter j. I'm just taking it in isolation. I don't care about anything else, so that it's just in 1D. And then I'm going to take small steps towards the minimum. This is what the algorithm looks like. And as you can see, the gradient will usually gives you steps away from the minimum if it's a parabola, or if it's just any kind of you're standing on a hill, and the gradient will just give you the vector that's pointing away from the minimum of the hill. And so what you really want to do is take steps towards the negative of the gradient, right? And you want to take step 1, step 2, step 3 until you get to the optimal solution, or the optimal theta, which is what I'm going to call here theta hat j. All right, so this is called the gradient descent algorithm. And really try to think, if this is the algorithm, try to think how would you, before you think how you would implement it, how would you write a pseudocode for it mathematically, right? You start from theta and you're updating theta. So you have theta equals theta plus some value, something that's a function of the gradient, obviously. And that gives you these small steps until you get to the best theta. So it's obviously an iterative algorithm. So how would you actually do that? Right? So it's while, not converge. So you have some kind of while loop, or usually for loop with a break in the for loop. So what do you do? Right? Think about it. Pause and think again. So it's theta j is equal to theta j minus alpha gradient of j with respect to theta j. Right, sorry, the subscript is j, the function is j. It's a bit confusing, but you get the point. Right, so this is what the gradient descent algorithm does. What it does is it's taking steps towards the minimum. Now, there are a few things we didn't discuss, like how do you actually implement that, but the size of the steps, you can take really big steps or relatively smaller steps, and this is controlled by what's called a learning rate here, what's alpha. Okay, and that's multiplying the gradient or the derivative of j with respect to theta, the parameter. Right, so this is going to be the algorithm that we're going to use not only in linear regression, but in a lot of algorithms. Actually, most supervised learning algorithms just use gradient descent or some version of gradient descent. Now that's great, but what is this derivative of j with respect to theta? How do you express it mathematically? How is it a function of h? First of all, j. Remember j. We assume that it's the square loss, and let's go with that for now. So if you replace h of theta in the square loss and you try to compute this derivative, what do you get? So this is going to be an exercise I want you to solve by hand. So get some paper and pen and look at dj d theta. And let's start simple. Let's assume you just have one xy pair, and that the hypothesis looks like this. It's y equals, or h theta equals theta 0 plus theta 1x. So how would you, what do you get? So replace this in j, in the expression for j, and then just calculate the derivative and see what you get, and see if you can just replace it back here and actually run the optimizer. If you're ambitious, try to code it up. For some simple example for data, create synthetic data and see if you can actually find the optimal solution. That will be taking multiple steps ahead. That would be great to think about first. All right, so we have gradient descent update in 1D, and now what we're really interested in is to scale it up for more parameters. We just looked at one parameter, theta j, or what if you have theta 1, theta 2, theta 3, maybe many parameters. So we'll go simple with just 2 parameters. And so what does the function look like if you have 2 parameters? Think about that. 3 to 1. It's a paraboloid, right? It's a parabola, but in 2D. It's just like, again, a ball shape. And it's a surface in 3D. The inputs, so that's, you can think of theta 0 and theta 1 as forming the floor. These are my two input parameters. So for example, the line that doesn't pass through the origin has two inputs. Theta 0 is the bias, theta 1 is the slope, and so you have, these are the two inputs, and the third dimension is just the value of j of theta, and that's square, so it's a paraboloid. And again, it's the same idea. We want to get to the minimum. And now the gradient, what does the gradient look like for j? So the gradient can be expressed like this. It uses the symbol nabla, and gradient of j. Try to remember what does this look like. It's a vector now of partial derivatives with respect to theta 1 and theta 0. And it's also pointing away from the minimum. So we want to take steps towards the minimum. How do we do that? So we just start randomly, some initial theta 0 and theta 1, and then we take small steps towards the minimum. And this is how we get the optimal theta. One way to understand and visualize this is to look at the paraboloid from above and to look at the contour plots. So I'm going to take this paraboloid and make sections for different values of j. So first, let's say for j equals 0.5, I'll take a section of this paraboloid. Actually, I don't know how you can see that I'm taking section, but I'll take a section for small j, then for j equals 1, I'll take another section, another section. So what do these sections look like? So I'm taking the intersection between the plane and the paraboloid. What does that look like? It looks like an ellipse. Right? So for small j, let's say j equals 0.5, you'll have the small ellipse, and then it's the bigger ellipse as you increase the value of j. So we get these contour plots, and now the gradient of j is just pointing away from the minimum. Right? So what does gradient descent look like here? If we look at everything from above, then it's just, again, vectors that are slowly taking small steps towards the center or the minimum. And we can now express it in vector form. Theta, how do you update theta? It's you take theta, you update it with theta minus alpha, the learning rate, times the gradient of j. Right? Very simple. Now, we looked at it for a given parameter, theta j. So if I just take theta 0 or theta 1, and I have this update rule, and we looked at it for 2D, and there was this nabla sign, which was the actual multidimensional gradient of j. Now, it turns out that, if you derived it, hopefully you got this expression for the gradient. So the derivative of j with respect to theta is actually this expression. So you had h minus y squared, and then when you got the derivative, there was a half outside, the half and the 2 canceled out, and then you have an x outside. And that's, of course, assuming that h is theta transpose x, right? So this is for one parameter, and you can actually loop through all the parameters and update each parameter separately. So for theta 0, this applies. For theta 1, this applies. For theta 2, this applies. And then you can do that one at a time. But you can also apply this algorithm in vector form, as I showed in the previous slide. And I want you to show that you can just stack all of these gradients. Right? You can stack all the thetas, theta 0, theta 1, theta 2, into a vector. And so you can stack all of these equations, and you'll end up with this expression, right, that we had before. So write it down and convince yourself that this derivative, this partial derivative, when you stack them with each other, you actually get this gradient with nabla of j. All right, so this is, again, now when you stack things, you'll end up with exactly the same expression as before, except that the main difference is that these thetas and the x here are vectors. They're not scalars anymore, and you don't have a subscript j anymore. Right? You stacked all of the parameters in one vector. And usually for implementation, this is much more efficient because internally you can deal with vectors, and you can parallelize much more easily, and so this is way faster. Now this leads to, again, the gradient descent algorithm, which we're going to call batch gradient descent, because what we're doing is we're looping through the whole data set, and we're updating theta every time we're performing a loop, and so we're taking these smaller steps. And this, capital T here, I'm going to call epochs, or this is for t equals 1 to capital T. So these are the number of steps you perform to get to the minimum. And this is the first hyperparameter, or actually the second one we're going to be introduced to. The first one was the learning rate. The second one is the epochs. These are called hyperparameters because they're parameters that are important for you to get to the minimum, but there are things that you have to choose yourself. They're not part of the optimization algorithm, right? The gradient descent optimization algorithm. So these are two things that you have to sometimes tune and choose yourself to actually get to the minimum you're looking for. All right, so now we've developed this gradient descent algorithm. We discovered that there is an algorithmic way of finding the minimum given a linear hypothesis. And this algorithmic way applies not only for linear regression. We'll see later it applies if your labels and outputs are binary, and even if your hypothesis is not linear at all, it's extremely nonlinear, it still applies. All right, so what's the problem with this algorithm? If you notice here, there's a sum over all the examples, I equals 1 to n, and let's say you have 100,000 apartments. So every time you want to take a step, you have to sum 100,000 terms. And then you find the steepest descent, you take a small step, maybe your alpha is not very large, so you take a very tiny step, and then you go back and you calculate this again. Once you update theta, you calculate this like 100,000, sum of 100,000 terms, and you make that update again. So that's too expensive if n is really large. So what's the solution to that? Well, it turns out that maybe instead of taking the sum over all the examples to actually calculate where you should take steps, in which direction you should take the step, it's probably better to just take one example at a time. So that's theta is updated, and I just completely removed the sum. So how do I actually think of that? Like, what does that even mean? So this new algorithm is what's called stochastic gradient descent, and now I'm looping over the epochs, and not only over that, within that I have a for loop over the examples, and within that I just have one example at a time. I calculate the gradient with respect to one example at a time. What is this really doing in this plot of a paraboloid that we had before? And so, as you can see here, I replaced the sum with a loop, a for loop over the examples. So stochastic gradient descent is this algorithm, and let's pause a little bit and think, in this contour plot example that we saw before, what does that even mean, right? Or in this plot here. Right? So what it turns out, what it means is that we're taking not a straight line every time we're making steps. That's not the optimal step that we're making towards the minimum. We're making some suboptimal step, but it's somehow towards the minimum because we're taking these examples into account, the examples of the data set. Right? So if we look at it in the contour plot from above, then this is just batch gradient descent, the normal type kind of gradient descent we saw before, and stochastic gradient descent will just be this random walk towards the minimum. And so clearly, you're going to have to take more steps to get to the minimum. So how is that better? I mean, it should be slower, right? Well, not exactly, right? Because we said the problem was that if you have n really large, you have to sum n terms to find the gradient, while in stochastic gradient descent, you just have one term, so it's really fast. So taking steps is really fast. So while you have to take more steps to get to the minimum in stochastic gradient descent, each step requires much less time. And so it ends up being that stochastic gradient descent in total is way faster than normal gradient descent. All right, so let's compare the two algorithms. Batch gradient descent is in green. It's taking you straight to the minimum, but each one of these steps is pretty slow. And stochastic gradient descent is much faster, but it's taking you through this stochastic random walking path towards the minimum. Right? And as you can see, the difference is just that there's a sum here, and here it's replaced with a loop over the examples. All right, so before I conclude, try to just pause again here and try to remember what we've done. We start with a data set. It was a table of numbers, and we decided there are some inputs and outputs. And we said that what we're really interested in is, given a new input, what's the output, right? And then we developed a hypothesis, a linear hypothesis. We made some assumptions, and we defined the cost function. And based on that, we optimized the cost function to find the best parameters, and we got the hypothesis back. So what's the point? Right? Try to think about it. What's the point? Why are we finding these hypotheses? Well, I just said it. You want to predict unseen data. And so let's summarize things a little bit here. Assume a linear hypothesis. We assume that H is actually theta transpose X. It doesn't have to be that way, but we assume that. And for this case, we define the cost function. We assume that square, again, it would still work if it's absolute loss. Gradient descent would still work in that case. And you can imagine other types of losses, maybe to the power 4. Would that be useful? I don't know. And then you can take that and minimize theta to find the best theta. This is going to be my theta hat. And this, we said, used SGD, or stochastic gradient descent. And finally, we took the best theta, this theta hat, and we replaced it back into the optimal predictor, or my linear hypothesis. So this is going to be H theta hat of X, or what would be a theta hat transpose X. And now you can take that to predict things that you haven't seen. So I give you now a new apartment size, and you'll tell me what's the price. So you get an X new, and then you pass it into your H, and you get your Y prediction. Right? And so this process applies not only to linear regression, but as you'll see, to a wide variety of supervised learning algorithms, if not all of them. And it always ends up being some kind of curve fitting, where you're fitting a function toward through a bunch of points, right? So, and this is what it's all about. Now, before I conclude, I want you to think about something, you know, when this video ends, before the next lecture. And the question is, why not interpolate to all the points? Right? So you've defined a loss function, and we've assumed that it's a line, and we thought that, okay, a line fits it really well, but we've assumed it's a line. Like what if you don't have that assumption? What if you can just fit any curve, just like we said at the beginning? So, you know, polynomial interpolation to all the points. And in this case, what is the loss? If I just have something that passes through all the points, well, clearly the loss is 0, right? Because there is no difference between what the hypothesis predicts and the actual data. Is this a good model? Right? Let's say I have a polynomial interpolation model, just a polynomial. So also, how many features do you need, or how many polynomial terms in this sum do you need to actually fit all the points? Maybe think about that a little bit as well. But let's say you fit all the points. What does that even mean? It's, you know, obviously the loss is 0. That's exactly what you want. Is this really what you want? Is this really the best predictor, if you're not assuming linearity in the shape of the function? All right, so think about it a little bit, and see you next time. Thanks.